Okay. So to be honest, I thought you were coming at this with no knowledge, but if you have some, that's great. So, tree diagram for probability. Right, there are two main words in probability that we need to be aware of,
Yes.
which are the word and or. And they kind of link the maths. So does anyone know if we have the word and, what do we do with probabilities? Yeah, give it out. You don't. Good guess though. You would multiply. If it's the word or, we add. Okay. And that's because normally people think the word and means you have more. Yeah? If you have fish and chips, you have two. But actually, if we talk probability, if I say to you, what is the probability of getting this and that, I'm actually limiting the number of outcomes. I've got less outcomes. So we're not adding things together. But if I said to you, you can have fish or chips, that means less. But with probability, if I said, what's the probability of rolling a 6 or a 4 on a die, I'm actually offering you more options. All right, so think of it in that way. So if we've got the situation where we have an and involved, we are going to be multiplying probabilities. The word or means we're going to add. So a tree diagram helps us to consider all possible outcomes, because with probability we have to consider all the outcomes. And if we don't consider all the outcomes, we may well get things wrong. We might consider things more than once. We might not consider something happens in more than one way, and so on. All right? Now, we also, with tree diagram, consider the fundamental rule of probability, which is if I consider all possible independent events or outcomes of an event, then the sum of their probabilities must equal what? Jesse?
0.
Nope. If I consider all possible outcomes, independent outcomes of an event, the probability of all of those added together must equal 1. 1, not 0. Because if I say to you, I roll a die and what is the probability of getting a 1, a 2, a 3, a 4, or a 5, or a 6? I've considered all possible outcomes, so that must be certain. I will get one of them. All right? However, if I said to you, what's the probability of getting a 3 or a 2? What would you tell me?
1/3 probability.
Pardon?
It's 1/3 probability.
It's a 1/3 probability, because I have 1/6 plus 1/6 makes 2/6. I'm talking to you as if you know all this stuff now, so stop me if I'm wrong. All right. So with our tree diagram is just about considering all possible outcomes, but we have to consider the outcomes also, their probability is summed to 1. So we've got this information here, and the setup is Hannah is going to play one badminton match and one tennis match. And the probability that she will win the badminton match is 9/10. The probability that she will win the tennis match is 2/5. All right, complete the tree diagram. So we've got badminton, tennis, right? So the probability that she wins the badminton is 9/10. The probability that she does not win the badminton is 1/10. Okay. Then we move on. The probability that she wins tennis is 2/5. Therefore, the probability she does not win it is 3/5. Now, does that change depending on what happened in the badminton? No. So I'm just going to check because sometimes it will say, like, if Hannah lost the badminton, she has even less chance of winning the tennis. All right? because maybe she loses confidence, maybe the person that beats her in badminton is definitely going to beat her at tennis, or, you know, that would be, they would not be independent events, it would become a dependent probability. But in this case, it seems completely independent of each other. So actually, we've got Hannah wins again is 2/5, does not win is still 3/5. Now, yes?
What's the purpose of having two tennis tree diagrams? Is it like, is one for badminton, but it's two for tennis?
Okay, yeah. So does anyone know why? We've got, what you said was we've got two options for tennis. Yes?
Because there's two possible outcomes for badminton.
Yeah.
For one, for when she wins, you have a possible outcome in badminton, and when she loses, you have another possible outcome in badminton.
Yeah. So how many possible combinations are there for win and lose? Well, with a tree diagram, we can see there are 4. So she either wins and wins, or she wins and loses, or she does not win and wins, or she does not win and does not win. Okay? So we have to consider all possible outcomes. So like Bradley said, there were 2 outcomes for badminton. There's also 2 outcomes for tennis. But because we're saying tennis comes second, there are 2 outcomes following 2 possible outcomes. So we have to consider it for all eventualities. So what is the probability Hannah will win both matches? So we have to consider the branches that she wins the badminton and she wins the tennis. So the probability will be badminton and tennis, she wins both. So we are going to do 9/10, 2/5, and what do I do in between? I multiply. Okay, so the probability becomes 18 over 18 out of 50. Right? Now with probability, you might want to add this as a note. It's not necessary to simplify the probabilities, unless it specifically asks you to, but they normally don't, because that's tested in something else, it's tested within fractions. They don't ask you to, because actually, when you add probabilities, you have to have the same denominator. So if you start cancelling at this stage, you're probably going to have to put it back to the old denominator anyway, to when you start adding. So that's the probability for winning both matches. Alright? Nice and easy. Does that make sense?
Mm-hmm.
Okay. Now, there is the second question. I'm going to go through this one, then I'm going to stop and I'll let you carry on. Now, this question has something very particular about it. And it's this line here. He does not put the marble back in the bag. Okay. So this time, what happens first affects what can happen second. Alright? Does that make sense? You've got to read this very, very carefully. And it's very nice because they've given you a helping hand like they normally do. Right. So we complete the tree diagram. So we have 5 red marbles and 3 green marbles. So we've got 5 from 8 red. So our green will be 3 from 8. Right? Has to add up to 8 out of 8 or 1. Now, that's taking the first marble. Now remember, he does not put the marble back in the bag. Right? So, could someone explain why getting a red marble the second time around is now 4/7 instead of 5/8? Jesse?
Because you take away 1 from the numerator and the denominator to symbolize the marble being taken out of the bag.
Yes.
Because there's 1 less option to choose from.
Yeah, so we've got 2 things there. So we were talking about the tennis having more than 1 option. In this case, it's even more relevant because the 7 represents, well, if a red one got taken out, we've now only got 7 marbles. All right? There were 5 red, and this option is a red one was taken, so now there are only 4 reds. Whereas there are now still 3 greens, but there's only 7 in total. Alright. Now this is where people can make a mistake, because they just always think, well, I'll just copy those two here. But actually, what is the probability of getting a red one if I got a green one the first time round? Tyler? Getting a red one if I got a green one first. So for a start, we know it's out of how many marbles? 7. And how many of them are going to be red? No. How many reds were there to start with?
5.
If I took a green one out,
So
how many are there still?
Still gonna be 5.
There's still going to be 5. Okay? Bradley?
Oh,
You got how many greens, Bradley?
2 and 7.
2 out of 7. Because I took a green, so I have to take one away from the amount of green, that gives me the 2. I have to take one away from the 8, gives me the 7. Okay? So you can see the routes that have been affected. Well, if I took a red first time round, yeah. If I took a red, then the red one is the one that gets affected. If I took a green, then the green one is the one that gets affected. So it's that, obviously the denominator changes, but the numerator is the one that gets affected depending on where we've gone. Alright? So this is dependent probabilities. So then we say, work out the probability that Dwayne takes marbles of different colours. So, yeah.
So you do the probability of the first one if he picks a red, then if he picks a green.
Yeah, exactly. So I would do my red. If I took a red, the next option would be taking a green. So that's one of the options. So I would do, he takes a red and he takes a green. So my answer would be
15 or 56.
6. Okay. But there is this option, or, which means we're going to add. The other option is
Green,
a
red.
green followed by. Oh, my thing's. Okay. So the probability for this would be
Same thing.
3 eighths multiplied by 5 sevenths. Now you will notice that that is
Exact same thing.
the same answer. Okay. So what is that? So I've got that or that. I add them together and I get the answer
30, 56 out of 56.
30 from 56.
Okay.
Yes.
You can also simplify to 15, 28.
Do we need to? Does it tell us to?
No.
Yeah, you'll notice again it doesn't say has to be. So I say with probability, I'm happy. You can be happy just to leave it as 30 out of 56. Okay. Unless they specifically say. Now, there are certain questions that they could ask you for. Alright? For instance, what if I were to ask you, what is the probability of getting at least one red? How many options is that? Just
3.
3, because they would be?
Get a red and a red.
Yeah, red, red,
Red and a green.
red, green,
Or a green and a red.
green, red. Now this leads me to one other thing that maybe we didn't work out, which is if I had to do the probability of at least one red, that's 3 options, yeah? Is that what you would do? You'd work all 3 out and add them together. Are you happy with that? Is there any other way that might be slightly more time efficient? Do you think? Well, what if I did this? I would do the probability, I would do 1 minus the probability of no reds. So I would work out the probability of green, green, and then subtract from 1. Why would I do that? Yep.
And what is all the probabilities? So you're subtracting that just green from all the possible probabilities.
Yeah, exactly. So if I work out all 3, that only leaves 1. So all 3 have to add up with this last one to make 1. So if I worked out that 1 on its own and took that away from 1, I'd be left with the other 3 all added together. Now in this case, that's not particularly strenuous to do the 3 and add them together. Alright? However, sometimes tree diagrams have 3 options for each one, for instance, and there might be a lot more possible combinations. Okay, so this is an important one. Alright, just checking the 1 minus probability. And this, just for your notes, for your vocabulary, this is the complement. So we say at least 1 red, no reds, they are the complement. That's 1 is kind of the opposite of the other. And then the complement and its event always add up to 1. So if you see in your reassessment, for instance, that word complement, you know what it means. It means, so what would be the complement to rolling a 6 on a die? Now what's the complement to it? So the actual event. So the probability of rolling a 6 on a die, the complement to it would be the probability of not getting a 6, yeah. Not a 6. Which you know as a 1, a 2, a 3, a 4, a 5. Alright? And I think as you said, Bradley, that is 1 out of 6, so this would be 5 out of 6. You gave me the probability. It's just stating what it is. So actually the complement is very easy. So if I had a pack of cards and I said, what's the probability of getting a king in a pack of cards? What's the probability? What's the complement, sorry, of that? You don't know cards? So we need to sort that out then. We don't even need to know. I just want to know the complement. Not a king. Yeah? We just say not a whatever. The probability of getting a king in a pack of cards is there are 4 from 52 cards. Okay, so the probability of not getting a king is 48 out of 52. No one know cards. Some of you need to, if you haven't experienced cards, you need to kind of have a flip in. It's such an obvious question to give you probability. Jesse?
Oh, I was just
You're just going to say you don't know or do know or you do know. Okay? Do you know what are the cards then? So we've got 52 cards. Okay? There are 4 what we call suits, which are the suits, diamond, well that's a club, a spade, okay, like that, and yeah, hearts, okay, and that's red, this is red, these 2 are black, okay, there's 52 cards, 4 suits, and the cards are, we have an ace, and then it's 2, 3, 4, 5, 6, up to 10. Then we have a jack, a queen, and a king. And these ones have a range of names from court cards, because they're the court, the kings and queens, they were in the court. That's why you would have a court jester, because they were. They're also known as face cards. Okay. We don't normally consider the jokers as part of the 52 pack. They're not. They're added to the 52 cards. So unless you're told there is an extra one, but that's what pack of cards would be. Right?
It's kind of awesome. Do you know why card companies put jokers in the deck?
Some games need them. I I don't know. I'm not a really big card, but I know that some games have jokers and they need to use them. So. Okay, so I think we've kind of covered enough, especially if that's a bit of a recap. Have a go at the rest of those tree diagram questions. If everything's good, we'll move on next time.